Let's try to solve a Leetcode problem today. So today let's try to solve 2385 amount of time for binary tree to be infected. Let's first try to understand the problem. So we are given the root of a binary tree. So here is the root, and this is the tree node, and the binary tree with unique values. It means inside the binary tree, the values of the node is unique. So for example, this is 1, 3, or 5, but there's no duplicate values. And we are also giving an integer start. So this is the starting point. So for example, this is the starting point is 3. And at minute 0, an infection starts from the node with the value start. So it means from the time 0, so we are at here at node 3, and this node is infected. So at time 1, so the other node, maybe 1, 10, and 6 will also be infected. So this is just the question. So for the next minute, let me try to use another color. Yeah, so for the next minute, this 3 node would be infected, and for the next minute, this node will also be infected. So this is a typical BFS problem, but we are giving the root of the tree. But the starting point is not always coming from the root. Sometimes the starting point is coming from other node, for example 3. Yeah, so the node is currently uninfected. Yeah, so this node 3 can infect other node. The condition is that this node is not uninfected, and this node is adjacent to an infected node. So this node 1 is adjacent to node 3. So we can use BFS to solve the problem. Yeah, so we're gonna return the number of minutes needed for the entire tree to be infected. Yeah, so for this example, let's try to check this example. So minute 1, minute 2, 3, and 4. So the answer would be 4. Yeah. So the first step is we're gonna try to turn this tree into a graph, because we don't know which is the starting point. If we turn the tree structure into a graph structure, I mean adjacency list, now we can start from any point. For example, we can start from this starting point, and then we can use the BFS to calculate the result. Now let's just start the problem. Yeah. So we're gonna prepare an adjacency list. So it's gonna be the default data list. Now I'm gonna write a DFS function. Inside it's gonna be a node. So this is just a traverse of the graph. So if we can traverse the graph, basically we can build the adjacency list, and later on we can use this adjacency list to solve the problem. Yeah. So we're gonna check if node, and then if node dot left. So this means for node 1, node 5, if there's a node 1, and then if we have a node 5, so we're gonna build an adjacency list. So if there's a node 3, we're gonna build an adjacency list, and we're gonna build it according to this traversal of the tree DFS. So it's gonna be like the in order, pre-order traversal. First we are coming from this root node, and then left and right, and root left and right. So this is a typical pre-order traversal of binary tree. We can use this pre-order traversal to build the adjacency list, or you can also use other traversal of the tree to build the adjacency list. It doesn't matter. Yeah. Now we're gonna build it. So we're gonna use the values, because the value is always unique. So g not dot value can append not dot left dot value, and similarly g not dot left dot value, because we're gonna build undirected graph. Yeah, because if it is undirected, it's easier for us to check from this node 3, it's gonna infect all other nodes. So it's gonna be a undirected graph. So here it's gonna be the node dot value, and similarly we can also check the node dot right. Yeah, but after each check, if there's a node dot left, we're gonna run the DFS node dot left. Yeah. Now we can copy the same code for the node dot right. So here node dot value, it's gonna be the node dot right dot value, and this one gonna be the same, and the DFS should be DFS node dot right. Yeah. So after this we have an adjacency list. So it's gonna be this G, Now we need to prepare a weighted set for the BFS. So we are starting from the start node, and this start is also a value, and this start is a value, and inside of the adjacency list it will also be values. So this means we can use the BFS directly. So we're gonna prepare the queue. So inside it's gonna be a tuple. So the first element would be the start node, and the second element would be the distance, and finally we just need to return the distance. Now let's just check this BFS. Let's just run a BFS. So for the BFS, we're gonna check this queue, and we're gonna pop out the node and the distance of this queue. So queue.pop left. Now we are going to check the neighbors of this adjacency list. So for neighbor in G node, if this neighbor is not in visited set, so we're gonna put it inside of the queue. Yeah. First of all, the visited set would add this neighbor, and the queue should append a tuple of the neighbor and the distance plus 1. And finally, if there's nothing inside of the queue, we're gonna get a distance, and this distance is gonna be the maximum. Finally, we just need to return this distance because it's gonna always be the maximum. Yeah. Now let me run it to check if it works. If neighbor is not invisited, there's no is. If neighbor not invisited, yeah, it seems there's something wrong with the first testing case. It is 0, and for the second one it is 0. It is okay, but for the first one it is 0. It means there's something wrong. Let me check. Let me first check this adjacency list. Maybe something wrong with it. Yeah. Let me print out the adjacency list. So there's nothing inside of the adjacency list, but it should have something. At least it should have some numbers. It means that the adjacency list is not right. Yeah, because we didn't run the DFS. This is why. So let's run the DFS first. So the DFS would be the root. Now let's just check what's gonna happen. Now we have an adjacency list, so this means everything should be okay. Now let me just remove the print and submit it to check if it can pass all the testing cases. As you can see, it passed all the testing cases and it's pretty fast. Now let's analyze the time complexity. So this is just a DFS, and here is just a BFS. So DFS for the tree and BFS for the graph adjacency list. So the time complexity is E plus V. E is the number of edges, V is the number of vertices, or the number of nodes. So let's just check. So the number of nodes in the tree is 10 to the power of 5. But if it is a tree, the number of edges is 10 to the power of 5 and minus 1, because the edges would always be the number of nodes minus 1. So the time complexity is O(n). N is the number of nodes. Thank you for watching. See you next time.